So remember, derivatives are just the slope of a function. So we place the function here in the numerator, and we write in the denominator what we're taking the derivative with respect to. What that means is this function you can visualize as your y-axis, and this function as your variable as your x-axis, and you want to find the slope of that graph. There's more complicated systems where you might be able to swap out what you consider your x-axis because your y function can be written or includes multiple variables. But let's not worry about that for now. So here I have x to the nth power, x to some integer n. Could be x to the first power, which will be linear, x squared, which will be quadratic, x cubed, which will be cubic, and so forth. Now there's a very simple rule that allows us to take this derivative very easily. So we're going to explore that today. And obviously this shows up time and time again through many different engineering and physics applications. So if our function is y is equal to x to the nth power, and I'm trying to find the derivative of this, right, x to n, so then I can write dy dx, or I can write dx to the power n, because that's equal to y dx. And what I'm telling you is all I need to do is take that integer, multiply it by x to the nth minus 1, right? So if this is x cubed, the derivative of that would be 3, because n would be 3 in that case, 3x, 3 minus 1, so x squared, x to the power 2. So x to the nth power is equal to the nth power times x to the n minus 1 power. And I'm going to quickly show you why that is for a couple of simple cases, and then we'll look at some graphs. And then you just keep this in your toolbox. You don't have to remember exactly why it works, just know that it does work, and we'll build from this. So to think about why it works, we need to think back at how we look at slope. Slope is rise over run, right? The delta y over delta x, which is essentially what's written here. Now, unless your function or your y function is linear, then your slope is changing over any given x location. It's not going to be the same. So because of that, we need a way to write this as a function, right? You need to write the derivative as a function, as we show here. So I can use the concept of rise over run, but if I take a small enough step, then I can do rise over run at different increments and just piece them together. That's what this limit term over here does, right? So this is saying the derivative dy dx is equal to the limit as delta x approaches 0. So the step size that I take, right? So step size meaning I take 2 points, one at each edge of this small step size delta x, and I take the y right at some x plus delta x, some tiny delta x, minus y at the x location. So 2 y values separated just by delta x. So we can do this. And what does this notation actually tell us? Y x plus delta x means I would plug in x plus delta x into my function. This one says I would just plug in x into my function. That's all we do, right? And we simplify and see what my final solution is once I simplify it and then apply delta x approaches 0. All right, so let's do this for n equals 1. So when n equals 1, then I just have the linear case, y is equal to x, right? So then I apply this derivative definition. I say dy dx equals limit of delta x approaching 0 at x plus delta x. So I plug in x plus delta x into this equation, I get x plus delta x, right? So it's a simple equation. Subtract that by the function at x. So I take this x and plug it into this equation, and you just get x. So x plus delta x minus x over delta x from here. X minus x is 0. So I just get delta x over delta x, and those cancel out. So I just get 1, which if I look at this equation here, if n equals 1, I'll put 1 times x to the power 1 minus 1, which is 0. So x to the power 0 is just 1. So 1 times 1 is 1. That's how I got it. So the slope, which makes sense, because if you write this as a linear equation, mx plus b, the slope is the coefficient in front of the x value. All right, so let's take a look at if n is equal to 2. If n equals 2, then I have a y equals x squared. All right, so I'm going to use this same form of derivative and plug in my values. So I'll get x plus delta x, plug in here, I get x plus delta x squared, minus, plug in x into my y function, the x squared. So I get x plus delta x quantity squared minus x squared over delta x. Take the limit of that as delta x approaches 0. So I expand this x plus delta x squared. I get x squared plus 2x delta x plus delta x squared. Well, x squared here and x squared over here cancel each other out. So I'm left with 2x delta x plus delta x squared in my numerator divided by delta x. So I can cancel the delta x from each of these terms, and I'm left with 2x plus delta x. And I need to take the limit as delta x approaches 0. Well, that's easy. This term just goes to 0, and I'm left with 2x. Okay, let's do it for n equals 3. N equals 3 is my cubic function, and we know we're going to expect this to be n, which is 3, times x to the 3 minus 1, or x squared. So we expect the derivative of this to be 3x squared. So let's take a look at what the equation gives us. So we got dy dx is equal to x plus delta x cubed minus x cubed, right? Hopefully you see a pattern now, divided by delta x. Expand this cubic using Fibonacci's triangle. Then we get x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed, right? So that's the full expansion minus x cubed from the yx term. So just focus on the numerator for now. X cubed drops or cancels out, so I'm just left with these 3 remaining terms here. So I got 3x squared delta x plus 3x delta x squared plus delta x cubed over delta x. So I could divide by delta x for each of these, for each term. Then I'm left with 3x squared plus 3x delta x plus delta x squared. Take all of that at the limit as delta x approaches 0. So the first term stays, the second term drops out, third term drops out because you have a delta x in there, and we're just left with 3x squared. So you can do this to the 4th, to the 5th, to any n value, and you're going to see the same thing, right? So you're going to get an x to the n plus n times x, n minus 1 times delta x plus a whole bunch of terms that are going to have a delta x in it, minus x to the n. The x to the n terms will drop out, and then you'll divide by delta x, and you're just going to be left with this term here. So now you have this rule. You can see how this looks like when we graph it. All right, so graphically, what does this all look like? It can help sink some of the concepts in a little bit better. All right, so we said if we have a linear graph, like we show here in solid, the slope is constant. So if I apply n equals 1, like I showed earlier, n equals 1, so 1 times x to the n minus 1, so x to the 0th power, so it's just going to be 1. So we get a constant. So the dashed line shows my derivative as a constant value, which makes sense. Let's take a look at x squared. X squared, if you think about the slope, right, you think about a tangent line running as you come down. You start off at a steep negative slope, and it gets shallower and shallower until you hit the minimum point at the origin here, where you're hitting a 0 slope. Then you're growing and growing and growing and growing, getting larger and larger. So the linear dashed line shown here as a derivative makes sense, right? So you start off negative out here, you reach the 0 or the minimum point of my function x squared, that's where we have a zero slope. And then it starts rising as you show here, right? So we have 2x is our solution. N equals 2. So 2 times x, 2 minus 1, or x to the power of 1. So 2x. Let's take a look at our cubic function. So in solid, I got my cubic function here, and it's saying that 3x squared is my solution. So 3 times x to the 3 minus 1, 3x squared. All right. So does this make sense? So let's walk along the cubic function, the solid line here, solid green line. So it's a starts off as a steep curve, so a large positive value as a slope, and it gets smaller and smaller until you reach your inflection point here at 0, and then it starts growing. The slope starts growing up here, right? So that's reflected by a quadratic, right? Starts off large, then it's decreasing until it hits the origin, the 0 point, where that's because of the cubic inflection point. Now it changes direction and it goes this way, right? So it makes sense that you would have a minimum at that inflection point. And we could do this for higher orders as well, obviously. All right, so we have x to the 4th, you're going to get a 4x cubed derivative. X to the 5th, you get a 5x to the 4th derivative. X to the 6th, you get a 6x to the 5th derivative. Now, on its own, it seems hopefully extremely simple, but we're going to add rules to these, and so this will be part of your initial building blocks. And as we add things, you can combine it. You look at larger functions, more elaborate functions, and you'll see the power of something like this. So we're going to keep adding some more derivative rules, and then we'll piece them all together and to look at larger, more complex functions.